So I'm really excited about the Nobel Prize in Chemistry, particularly because I've done research in that area. If you haven't seen the announcement, I'm talking about the discovery of quantum dots being awarded the Nobel Prize in Chemistry. And if you don't know what a quantum dot is, well, you're in luck because I'm a researcher who has studied quantum dots. Professors Bawindi, Bruss, and Eichemov were jointly awarded the Nobel Prize in Chemistry for their contributions in the discovery and improvement of quantum dot synthesis. Now that that's out of the way, quantum dots are a type of semiconductor nanoparticle. Nanoparticles are typically defined as objects between 1 and 100 nanometers, and quantum dots are usually on the lower end of that range and usually no larger than 10 nanometers. They can be made from a wide variety of materials as long as they have properties between conductors and insulators, i.e. semiconductors. So you can have quantum dots made out of single materials like silicon or germanium, or multiple materials like cadmium selenide, cadmium sulfide, or even things like indium gallium arsenide, mercury cadmium telluride. The list goes on. Quantum dots get their name from a property they exhibit called quantum confinement. An easy way to conceptualize this property is with this diagram. It describes the energy levels an electron can occupy in a material and how an electron can move in that material. In a bulk material, there's lots of energy levels that an electron can occupy, and the density of those electronic states is very high. But when you start to decrease the dimensionality of those materials, this all changes. When a material exhibits quantum confinement, the electrons and the holes that they leave behind are spatially confined. They're restricted in the ways that they can move around in that material. And you get this quantum confinement by limiting the number of electronic states that those electrons can occupy. And you do that by changing the actual dimensions of the material. So when you limit how the electrons and holes can move in one dimension, you get a quantum well. There's two other spatial dimensions that those electrons can still move around in. In 2 dimensions, you have a quantum wire. They can only move along unrestricted in 1 dimension. And when all 3 dimensions are spatially confined, that's when you get a quantum dot. Because when you limit the actual size of the material, you're limiting the number of electronic states that material or the electrons can occupy. And so you have these really discrete transitions or quanta that can only be occupied by an electron. And when this happens, you start getting really interesting behaviors in materials like light emission or photoluminescence. If you remember from chemistry, materials have a valence and conduction band, and electrons can occupy different energy levels within those bands. With quantum dots, what happens is when you have a high energy photon come in, it can excite an electron from the valence band to the conduction band, and then that electron will decay back to the valence band. But when it does that, it releases an energy. And the energy that it releases is the energy of the distance between the valence band and conduction band, and that's called the band gap. The energy that it gives off is in the form of a photon or light. And this energy is directly linked to the size of the nanoparticle. So when you have a larger quantum dot, it'll emit more red emission. And when it's smaller, it'll emit bluer emission. And so simply by changing the size of the material, you can get a bunch of different colors out of the material. This is what a solution of quantum dots looks like under normal room light. You can kind of see some different colors, and that means that they're absorbing different wavelengths of light. But they really show what they look like when you put them under ultraviolet light. These are quantum dots absorbing that ultraviolet light and then re-emitting light at their band gap. And what I've done with this image is I've made smaller nanoparticles and then let them grow over time. And so these different vials are consecutively larger nanoparticles. And you can see the emission or the light emission that they get is redder and redder. So simply by changing the size of the nanoparticle, I can get a bunch of different colors. And that's unlike typical fluorophores or light emitting molecules where you have to change the structure of the actual molecule. So as long as you excite a quantum dot with energy below its band gap, it will release energy at its band gap. And this just isn't limited to the visible range either. People have managed to synthesize quantum dots that can emit all the way out into the infrared regions of the electromagnetic spectrum. So because of these properties, quantum dots have been used in a broad range of fields. For example, as imaging probes for biology, in LEDs and microscopes and TVs, in solar panels, in detectors, the list goes on. If you're still here for the end of this, thank you for sticking around. And if y'all want a separate video exploring how quantum dots are made, let me know. As always, this is the Mad Bioengineer.